Alrighty, so this is written homework for week 13. We have 4 problems. First one is, like I said, going to be a little bit more conceptual as opposed to the others. A lot more explaining and just kind of drawing as well. At least that's what I did when I explained it. But we can kind of go ahead and start. So for problem 1, it says we have a scientist that's investigating the interactions between mercury and a new type of plastic they are developing. Describe how the scientist could find the surface tension of adhesion. So for part A, what would they do? They want us to describe a possible setup and measurements and calculations that we would need to make to figure this out. So how could we figure out the surface tension for the adhesion? Anybody have any ideas at all? Or is this one kind of like, because I remember last year, this was the one that people were really just kind of unsure about, just in general problem 1, not just part A, but yeah, like kind of like from an experimental setup point of view, like if you were in the lab, like what would you do? And this is why it was kind of weird, because we weren't sure exactly what to do with this problem. But yeah, this is kind of like what would you do in an experiment? What would you do in a lab? Like, would you get a beaker or something and like fill it up with some fluid and try to measure the surface tension that way, or what exactly would you do, right? So yeah, everyone, or well, I guess 2 people so far have kind of kind of on the right track there. So yeah, one way or another, you're gonna put it into some kind of tube or pipette or whatever, right? And you could fill it with a certain fluid, right? In this case, mercury. So we know that mercury has a surface tension of 0.465 newtons per meter, right? So after filling the tube with mercury, we could probably kind of like, I don't know, take a pipette, make some droplets of mercury on the surface of the plastic, right? We can fill it up with like a plastic tube, right? And then look at the meniscus, right? We can see if it's concave or convex. And that'll basically determine if your cohesive or your adhesive forces are stronger, right? So for example, if I just had like a plastic tube, filled it up with mercury, right? And actually, let me kind of do this. So if it's kind of like convex or concave, whether it looks like this, it looks like that, right? It'll tell us if the cohesive or adhesive forces are stronger. And then the mercury, we know, will form like a contact angle with the plastic. And we can then kind of like measure that contact angle and use it in the equation that we know, which is gamma A. I just like to say Y. I don't know. It's just easier to draw for me. But that's equal to gamma times 1 plus cosine theta of the contact angle, right? So that would be the equation we'd kind of use to figure that out for the adhesion surface tension. So essentially it's just filling a tube, right, with the liquid that you want to figure out the adhesion surface tension for, and then kind of examine the meniscus, look if it's cohesive or adhesive forces that are stronger, and then look at the contact angle. From that contact angle, you can then kind of plug it into this equation that we have here to figure out the adhesive surface tension. Yeah, and you can place a drop of mercury on a flat piece of plastic and do that as well. Yep, you could do that one as well, and that'd probably be a little bit easier as well. But I just figured I'd throw in like the meniscus and stuff, because I figured that's a important concept as well to know, because I know that was emphasized on one of the lecture slides about cohesive versus adhesive forces. But yeah, you can absolutely get like a flat piece of plastic, measure the contact angle of the droplet sitting on it. So you could just kind of like have this flat surface, right? Put the droplet there, and then measure the contact angle, right? So yeah, either way would work as long as you are sure that you can figure out the contact angle, and then you can plug that into your equation to figure out your adhesive surface tension. But does that make sense for kind of the experimental way to set it up? Either you can put it in a tube or put it on a flat surface and measure the contact angle, and then measure the adhesive surface tension from that. Does that make sense? Okay, cool. So for part B now, it's telling us if the adhesive surface tension was 0.8 newtons per meter, describe and sketch how the mercury would behave as a droplet on a surface and in a capillary tube. So if our adhesive surface tension is 0.8, and they said the interactions between mercury had a surface tension of 0.465. Well, what is this surface tension right here? What does that signify? Exactly, cohesion, right? So this is our cohesive surface tension, right? So if our adhesion is greater than our cohesion, how do you think it'll look like in a capillary tube? How would the liquid, how would that mercury kind of look like? Would it look like this, or would it look like that? This is why I drew the tube here, because I figured it would be important for part B, and then in general, it's just kind of an important concept to remember. And I'll make this easier. I can say just like, does it look like the first one or the second one, I guess. So we got one left tube. One, okay. One, okay, awesome. Yeah. So it will look like this, right? That's all you have to do pretty much for part B, and then you kind of have to explain it, right? So we can say that since the adhesive force is greater than the cohesive force, the mercury will kind of tend to spread itself out, right, along the surface of the tube in a concave manner, right? So the mercury will spread out along the surface of the plastic and bind to the surface instead of itself. So since adhesion is greater than cohesion, the mercury will want to bind to the surface of the plastic as opposed to itself. That's all you have to say pretty much. And that's a very kind of general description. So we know that the adhesive forces are greater than the cohesive forces because this surface tension or adhesive surface tension here is 0.8, and the cohesive surface tension was 0.4, right? So that's why we know that the adhesive is greater than the cohesive. Yep, no problem. But yeah, so it'll tend to spread out basically along the edges of the capillary tube, or just kind of attach itself or bind to the plastic as opposed to interacting with itself. And if we were to think about, this type of experiment, right, that Caroline mentioned earlier, if we were to have that, for example, how would that look like? This is totally unrelated, just kind of like, it is related, but it's just kind of a side note, just to see if you guys are 100% like understanding this stuff. And it's okay if you don't as well. Like we can go over that and explain it. But I just wanted to make sure. So on a surface like this, if we had adhesion greater than cohesion, how would the droplet of mercury look like? Or what would it look like? Yeah. Kind of like this a little bit more, right? Spreading out, same idea kind of, right? Along the plastic surface and binding to the surface as opposed to itself. Now, if it was, so this is adhesion greater than cohesion, right? Now, if it was, well, I guess I'll save that for part C. But does everyone get part B? Because part C is basically asking us the opposite of this. Make sense? Cool. So, part C, it's saying if the adhesive surface tension was now found to be 0.2 newtons per meter, describe and sketch how the mercury would behave as a droplet on a surface and in a capillary tube. But yeah. So, oh, this is interesting. My bad. I actually read this part incorrectly. So, they actually do want you to draw this as well. So my bad. For some reason I looked at the capillary tube only, but hey, did it. Cool. Alrighty. So yeah, this is basically asking the opposite of what we did for part B. So now we have the adhesive is 0.2, cohesive is 0.4. So that means that the adhesive is less than the cohesive, right? So what would that look like in a tube? Kind of already, by process of elimination, it's not 1, so it's probably 2, right? So it'll look like this, right? So adhesive surface tension is less than the cohesive surface tension. So cohesive forces are stronger, right, than the adhesive forces. So the mercury will kind of repel the surface of the plastic. It'll quote unquote bead up, right? So it'll form that little bead, interact with itself a lot more. So as a simpler explanation, we can just say that since cohesion is greater than adhesion, right, mercury will not spread out along the plastic surface. Right? Mercury will tend to bind to itself. And basically clump together. In a convex manner. So cohesion greater than adhesion, mercury will not spread out along the plastic surface, right? Because cohesive forces are greater than the adhesive forces. So mercury will bind to itself, it'll bead up, right? Clump together in a convex manner, right? And you can kind of color this in if you want, just to kind of show, like here, this point right here, that point right there. That's what I did. Same for this part. I colored it in kind of just to show the the liquid, and here's my 2 points, just indicating that it'll spread out along the edge of the capillary tube, basically. And then for droplet on a surface, right? How would that look like? If the adhesive was less than the cohesive forces. Yep, kind of round bead, right? It'll clump up a lot more. But yeah, just kind of small explanations and little drawings for parts B and C, and in A, you can kind of explain the setup here, and have a drawing as well if you would like. But all you need is just kind of a description of how you would set it up. But we already kind of described that. Just so you can get like a tube, like we said, fill it up with the mercury and observe the meniscus, right? If the cohesive or the adhesive forces are stronger, and then measure the contact angle, right? Plug that into the equation, and calculate for your adhesive surface tension, right? Same thing for the plastic surface, right? You can do the same thing. Droplet on a plastic surface, measure the contact angle. There you go. But yeah, I would not just have the pictures there, just the drawings. I would also include a small description. But hopefully A, B, and C make sense. And I will be sure to kind of upload these on the Google Drive just in case you kind of want to go back and review them a little bit more. Because, I mean, you've been doing really awesome with the explanation so far. So that's great, because last year I remember like no one had any clue how to do any of these, because we were like how would you set it up, and I don't know, I guess we were not as smart as you guys. So but hopefully A, B, and C make sense, and like I said, I'll just upload these on the Google Drive as a reference, and hopefully that'll help as well. Oops. So any other questions or concerns about problem 1? Nope. Okay. We can probably move on to problem 2 then. Oh, actually, what happened there? I don't know why this erased. But yeah, let's just beat it up a little bit more. Anyway, problem 2, fluid film. So we have this question saying you are investigating the properties of an unknown fluid. You create a flat film using the apparatus to the right, which has a rigid U-shaped frame and a light movable pin. The frame is oriented vertically, as shown in the figure, and you find that if the pin has a mass of 30 milligrams and a length of 2 centimeters, that it experiences an upward acceleration of 26.8 meters per second squared. So pin, 30 milligrams, and length of 2 centimeters experiences upward acceleration of 26.8. Okay. So part A is asking us for the cohesive surface tension of the fluid, right? So we're just looking for gamma, right? Now, how can we come to this value based on the information given to us? So we have mass, right? We have the length, and we also have acceleration. Any ideas as to how we can go from this information here to something a little closer to gamma? Because remember, we can relate gamma to forces of tension, right? We know that gamma is equal to what? Yeah, exactly. So gamma is equal to force of tension over the length, right? Well, how can we calculate this force of tension? Because we have the length, right? Or we can get the length at least, right? So we know that the length is 2 centimeters. But after that, we have mass times acceleration. Yep, exactly. So we can start writing a net force equation, right? So we know that this is mass of the pin times the acceleration of the pin, right? And then what could that equal? So force of tension, right? So we have force of tension, and then we also have what force kind of acting to oppose the force of tension? Gravity, right? Now, there is one thing though. Is this all we have for the equation, or should we have an extra term here? So we should have an extra FT, right? Because there's the front and the back of the film, right? There's the force due to the gravity downward, right? And then the two surface tension forces, both pointing upwards, but it's one from the front and one from the back of the film, right? So it's kind of like, if you were to imagine it, if you were to kind of draw a free body diagram, it'd sort of kind of look like this. So force of tension there and another force of tension here, right? And then gravity pointing downwards. That's kind of a little impromptu free body diagram. You don't need to draw one. It's just, it might help you kind of visualize it a little bit more. But yeah, so once we have that, we can basically say this is 2ft, right? Minus fg. And then we can further simplify that by just rearranging this equation around, right? So we know that ft is equal to gamma times L, right? Times the length. So then we can say 2 gamma length minus fg, right? Is equal to mass of the pin times the acceleration of the pin, right? So that kind of puts things into a better perspective, right? So we have the acceleration that we had, we have the length that we can figure out, right? And then masses will factor in as well. But most importantly, we have this gamma that we're looking for, the cohesive surface tension that we can figure out, right? So essentially, we're going to try and solve for gamma. So what is next? We have to basically rearrange the equation to isolate the variable. So we can have 2 gamma L is equal to mass the pin times acceleration of the pin minus mg, right? So this is fg is just mg. And then divided by 2 times the length, right? So essentially it's just plug and chug from this point, because we know the mass of the pin is what? 30 milligrams. So that's about, I think, if I'm not mistaken, 3 times 10 to the negative 5th kilograms. Yeah. Oh yeah, and then thank you, Farah, for confirming. Yeah, so the mass is 3 times 10 to the negative 5th kilograms, right? Because we want SI units. Yeah, go ahead. Oh yeah, it's adding. My bad. Thank you. I'm sorry. Yes, yes. So you added over. I just, for some reason, I kept the negative sign. Yeah, absolutely. We would be plus mg. My bad. And thank you for catching that mistake, because I seem to be making a lot of mistakes today. But what you can do to kind of simplify things and not make this really long is you can kind of factor out an m, because the masses are the same, right? So you can say like m times a pin plus g, right? So you can keep the mass on the outside and then just add up the two accelerations, which is just like 26.8 plus 10, right? 26.8 plus 10, because it'll be the acceleration due to the acceleration of the pin plus the acceleration due to gravity, right? And I'm just omitting the units for now because they're both meters per second squared. But then we can just divide by, if this will probably do it there. Okay, it won't. Never mind. 2 times the length, which was what, 2 centimeters? That's just 0.02 meters, right? And then from that we can calculate the cohesive surface tension. And I apologize for past videos and this video if you hear like creaking or like loud banging noises or whatever. I just have the best neighbors of all time. Yeah. So someone already knows, Anna. Yeah, I guess you're familiar with the stairs. Some creaky stairs. All right. Yeah. I apologize for that. I wish I could probably go and try and edit it out or something, but yeah, that's an extra amount of time that I have to put into to make sure that it's edited out and then uploaded to Google Drive and YouTube. But yeah. Okay, great, because I mind it. Like, I'm trying to explain, and these people will not calm down. But did anybody get a value for gamma? See, I wish they were just rearranging furniture or something, but legit they're just walking around. But they're walking loud as hell. And it's all day. But, yeah, 0.028, 0.0276, about what I got. Newtons per meter, right? Yeah. So that's part A, right? So that's how to calculate the cohesive surface tension. So we kind of recognize first that we can relate it to force of tension or length, right? Relating to one of the values that we have. And then we can go from there and figure out force of tension by writing a net force equation, right? From that, we kind of manipulated variables and whatnot to figure things out. But most important thing, I think, I personally overlooked when I was, doing these practice problems or submitting the homework or taking a quiz or whatever, is the fact that there's two forces of tension, one for the back and one for the front, or one for the top and one for the bottom or whatever, right? But generally we kind of see like a problem like this set up. Usually it's going to be factoring in two forces of tension, back and front, bottom, top, so that's really important to look out for. But hopefully part A made sense. Are we all good to move to part B? Yep, okay. So part B is saying a droplet of this fluid with radius 4.6 millimeters is dropped from a pipette at sea level. What would the gauge pressure inside the droplet be? So need to figure out gauge pressure inside the droplet, right? have radius, right? So this is radius of what? What does this radius value kind of match up with? Whatever value we know. So radius of the droplet is technically our radius of curvature, right? So this would be, convert it to SI units, would be 4.6 times 10 to the negative 3 meters, right? That's our radius of curvature. So, once we have our radius of curvature here and we have pressure, or we're trying to figure out the gauge pressure, right? So, we have this droplet, right? Imagine like a droplet. What is this? They just said fluid, but if we can imagine like a droplet of water, right? So we have what pressure acting on the outside? What do we know for sure like that pressure value is supposed to be on the outside? Exactly, 10 to the 5th pascals, right? Which is just the atmospheric pressure. So if I'm trying to figure out the gauge pressure, right? P gauge, well, we know that that's the absolute pressure of like the inside, right? So whatever the fluid is, and then minus atmospheric, right? We just know that as a general, definition, that the gauge pressure is equal to the absolute pressure of whatever fluid, fluid's pressure that I'm calculating minus the atmospheric pressure, right? So the fluid pressure, right, would just be P in, right? So P in is the fluid pressure, which is on the inside, right, because it's a droplet, and the outside is the atmosphere, right? So if P in is the fluid pressure, basically, and P out is atmospheric, well, then we can kind of use what equation to kind of relate P in and P out? Oops. Exactly, so Laplace's equation, right? P in is equal to P out plus 2 gamma over radius of curvature, right? So that integrates all the values that we have. We have radius of curvature that they gave us. We can throw that in. And then we can use the gamma that we had from before, throw that in. And then understanding this definition here, that P gauge is P absolute minus P atmospheric, right? This absolute pressure is the fluid pressure, right? So that's P in, and then P out just happens to be the atmospheric pressure, which is the same as what's included in this P gauge equation, right? So if we just subtract this over, P in minus P out is equal to 2 gamma over the radius of curvature, right? Well, then this just becomes P gauge that we want, right? So this is just P gauge. So P gauge is then equal to 2 times our surface tension from before, which was 0.028 newtons per meter, and then divided by our radius of curvature, which was like 4.6 times 10 to the negative 3 meters, right? So that should give us a P gauge of what? Yep, about, I had 12.2, I think. And that's newtons per meter squared, which is technically 12.2 pascals. And let me check that real quick again, just to make sure that I didn't throw something wrong in my calculator. But yeah, 12.17, 12.2 newtons per meter squared, or 12.2 pascals. Mm-hmm. Okay. So yeah, because I typed it in again, and I made sure just because I didn't do 4.6 times 10 to the negative 3. What I did is just like 0.0046, which is the same thing, but I thought maybe I'd like threw in an extra or less or 0 or whatever. But yeah, I got 12.2 pascals or newtons per meter squared. But any questions about part B? Makes sense? Okay, cool. Part C is saying the droplet falls on a horizontal sheet of plastic, making a contact angle of 125 degrees. What is the adhesive surface tension? So this is kind of a throwback to problem 1 here. It's just going to be really just plug and chug, honestly. So we have the adhesive surface tension times our cohesive, or is equal to cohesive surface tension times 1 plus cosine of the contact angle, right? So that's that equation that wrote down up here, right? So we can just throw in our 0.028 newtons per meter, right? Times 1 plus cosine 125 degrees, right? And that should just give us our adhesive surface tension there. And let me calculate it as well, just to make sure, double check my answers. And I got around 0.012 newtons per meter. Yep. 0.0119 as well. Yep. And that should be your adhesive surface tension there. And this is a pretty simple plug and chug part right here. Just asking for the adhesive surface tension, so you can relate that to your cohesive. Cohesive times 1 plus the cosine of the contact angle should give you your adhesive. All right. If there aren't any other concerns or questions about part C, we can probably move into part D. Part D is pretty simple too, just quick, easy explanation actually. Shouldn't be more than like 1 or 2 sentences. But part D is asking or saying, suppose you wanted to increase the contact angle, could you do so by changing the type of plastic in the sheet, changing the adhesive surface tension? If so, should you increase or decrease adhesion? Explain your reasoning. So if we wanted to increase the contact angle, right, how would we do that? Would we change the plastic, change the adhesive surface tension? What should we do? If the angle increases, the adhesion actually decreases. So basically what this is saying is like, I'm going to increase the contact angle regardless. I'm going to increase it, right? So if I want to increase it, how can I do that, right? Would I change the type of plastic or the type of material, basically, and then thus changing the adhesive, or changing the adhesive surface tension, sorry. But, I mean, if you think about this equation, right, if you think about the adhesive surface tension is equal to the cohesive times 1 plus cosine of the contact angle, right? If you remember, like, there was a slide in the PowerPoint, I believe, where it was saying, like, different materials or mediums will have different contact angles, right? So, if you were to just to kind of like throw in some sample values, right, and calculate this out, you'd notice that if you increase the contact angle, you actually decrease the adhesive surface tension. So if we just threw in like the same values as before here, right, for 0.028 times 1 plus cosine 125, if we just made that cosine 130, for example, right, you'd notice that it would drop down from 0.012, I think it was, right, to just 0.010, right? So if I increase the contact angle, I'm going to be decreasing the adhesive surface tension, right? So the way that I can increase the contact angle is by changing the type of plastic or type of material that comes into contact with like the fluid, right? So if I change the type of plastic or the material, we could change it to where it increases the contact angle, therefore decreasing the adhesive surface tension. So increasing the angles by changing the material, that would give less adhesion. Yep, exactly. So if I wanted to increase, right, actually let me type this out because it's just because I'm a lot slower writing things. But if I increase my contact angle, I would want to change my material or medium, right? Thus, this would change the adhesive surface tension. The adhesive surface tension would then decrease with an increasing contact angle. So changing the material would allow you to increase that contact angle, and then increasing the contact angle would decrease your adhesive surface tension. It's in my opinion, it's such a poorly worded question, because like I remember last year not being sure like what exactly were they asking. Like, I mean, I know they want us to increase the contact angle, but it's like, what are they asking here? This part. Like, I guess this comma and like right here, this part here is just weird to me. I don't know. Just grammatically, the sentence is just structured or formulated in a weird way, in my opinion. I don't know. Maybe I just suck at English, but if you understood it, great. If not, hopefully this kind of made a little bit more sense as to what they're asking. It's that for sure I want to increase the contact angle, right? That's what I'm doing. How can I do this, right? The how is basically by changing the material, right? So if I change the material, the type of material that I'm using, I can change the contact angle. So changing material will change the contact angle, right? And the fact that the contact angle is changing will result in a change in the surface tension and the adhesive surface tension. And then the second part here is basically saying, well, if it's going to change, right, then is it going to increase or decrease? And so if you go by this equation, it'll basically show you that it'll decrease with an increasing contact angle. Right? So that's basically what it's saying. So I guess maybe like if we were to kind of read this question here. So could you do so by changing the type of plastic in the sheet, changing the adhesive surface tension? So I guess what they mean here with this comma right here is just basically like this sentence right here is just basically saying like, okay, could I increase the contact angle by changing the type of plastic in the sheet? And then by doing that, change the adhesive surface tension? I guess that's probably a way of rephrasing the question. Yes, this is practice for cars on the MCAT. I don't like this question. This is not phrased properly. I don't like this comma right here. This comma just makes things confusing. Maybe it's just me, but it's just saying that could I change the contact angle by changing the material and thus change the adhesive surface tension? That's basically what it's saying. And if I can do that, would I increase or decrease adhesion by increasing the contact angle? Hopefully that is a better phrased question that is easier to understand, or maybe you just understood the original question. And in that case, you are a lot better at English than I am. Yeah, so you know what, because just because I feel like it, and because I feel like this question is just not the greatest, I will go ahead and rephrase it. This is just my like obsessive tendencies here, so don't mind me while I go ahead and rephrase the question as I wish. Okay, hold on. Let me actually, I think the first part was okay. Say wanted to increase the contact angle. There. I think I might be still grammatically a little bit off, but hopefully it makes a little bit more sense. Changing material would allow for a change in adhesive surface tension. A decrease in the adhesive surface tension is related to an increase in the contact angle. Yeah, that's good. Yep, that makes sense. Yeah, so hopefully that's all fixed. I will label this as rephrased question in case people get confused. Yeah, okay. Sorry about that little, I don't know what that was. That was just me caring too much, I suppose, but I just didn't like the question. So hopefully that made sense for part D. But yeah. Oh wow. See, this is what I'm telling you about my grammar. Hold up. I'm goofy. I put a period instead of a question mark. There. Perhaps this is more grammatically correct. All right. That's it. That's all I'm doing. It's the end of my grammar tirade. All right. So, any questions at all about problem 2? Or are we good to move on to problem 3? Makes sense? Okay, cool. Okay, so problem 3, IV bag. So this is like one of those MCAT problems where it tries to relate to physics for just no good reason. So it says a 3 centimeter long needle at the bottom of a tube connected to an IV bag is used to inject 125 milliliters of saline solution located 70 centimeters above the needle over a 1 hour period. The viscosity of the saline solution is 1.1 millipascal seconds, and its density is 970 kilograms per meter cubed. You may assume the resistance to flow and fluid speed in the bag and the tube are negligible. Yeah. So only the resistance across the needle needs to be taken into account. All right. So part A is asking if the veins gauge pressure is 5 millimeters of mercury, what will the difference in the input and output pressures be across the needle in both millimeters of mercury and pascals? So we're looking basically for delta P in pascals and millimeters of mercury, right? We know that the veins gauge pressure is 5 millimeters of mercury. And then, and then the height is 0.70, basically. So, we have the top here is P atmosphere. This bottom here is some pressure, right? You can say this is PA, this is PB, right? The height here is 0.70, and we're trying to figure out basically like what is PB minus PA or PA minus PB or just delta P basically, right? So we have values of height, we do have values of density, right? And all that type of stuff. So any ideas as to how we can relate pressure or pressure differences with height values that they gave us and densities and whatnot? What equation do you guys think we can use to determine the change in pressure here? Yeah, excellent. Hydrostatic pressure equation, right? So we have PA plus rho GHA is equal to PB plus rho GHB, right? And then we can kind of plug in things, to the equation. So first of all, we have PA, right? PA is what? This is P atmosphere, right? So they gave us gauge pressure for the vein. So instead of like converting from absolute to gauge and gauge to absolute, we can just honestly just throw this in here. PA is 0, right? So 0 millimeters of mercury, 0 atmospheres, technically I guess, and basically 0 pascals as well for our gauge pressure there, right? So throw that in. And then we have our density, right, of the saline solution. We know that to be 970 kilograms per meter cubed. We know the acceleration due to gravity is 10 meters per second squared. And then the height at A, right, the height at A, we can label that to be the 0.70 meters or the 70 centimeters, right? And this is my personal preference, but when I have PA and PB, I just think of B as my bottom value, right? So I this is just me, but I always set my PB, or my second value right here, the one that's at the bottom, as my 0. And then whatever's at the top would be my height, basically, and that's 0.70 meters, right? The reason I do that is then you have things in the positive y-axis, right? So just kind of makes things easier. But yeah. So 0.70 there, right, for my height at A. My pressure at B was the 5 millimeters of mercury, right? And thing is, this equation is all in SI units, right? So any conversion that they want us to make to get the millimeters of mercury at the end, we'll have to, like, basically we're going to convert and then reconvert. So I have 5 millimeters of mercury. That's not going to cut it when I'm doing my equation here, right? What I want to do is convert it first to pascals so I can have my SI units all in order. And then whatever answer I get in pascals, that checks out. And then I can convert from pascals to millimeters of mercury again at the end to make sure that I have both millimeters mercury and pascals. So 5 millimeters of mercury, yep, is 6,790 pascals. Anybody need like a refresher or an explanation as to how we can go from millimeters of mercury to pascals? Or you guys can, okay, you got it? Okay, alrighty. So 5 millimeters of mercury, right? In 1 atmosphere, we have 760 millimeters of mercury. And then in 1 atmosphere, we have 10 to the 5th pascals. That's how you can go from millimeters of mercury to pascals. So millimeters cancel millimeters, atmospheres cancel with atmospheres. You're left with pascals on the top. Yep. So that should give you 6,790 pascals. I think, yeah. Actually, let me check real quick. My bad. Actually, I totally got confused there for a second. So it is not 6,790. 6,790. 6,790 is actually like the answer for like the pressure for B, but the one second here. Actually, wait, am I? No. Okay, hold up. I'm just being stupid. 5,760 times the 5th. Okay. Yeah. Yeah, I got 657.9 as well. Yep. So 657.9 pascals, right? And then, okay. So, let me read this one more time because I think I'm missing something, but, yeah, no, 657.9 is 100% correct. It's just that now I'm just wanting to make sure. So if we actually carry this out, so we have PB, right, plus PGHB, and HB, right, we said that was 0, so this whole term will cancel out. So we'll just be left with PB. This is going to give us 6,790, I believe, for PB. So if we take 970 times 10 times 0.70, yeah, that should give you 6,790. So okay, so 6,790. All right. So we have these two values here. Ah, my bad. I just completely forgot what we were asking for in the first place. So we're looking for a delta P, right? So I think I mistakenly, this is why I got confused. I think I mistakenly said that it was going to be PB minus PA, which is just not right. What I meant to say basically was that it's just going to be like the difference between like your vein pressure, gauge pressure, right? And then like, so like your input and output basically. So the pressure difference between this value here and this value there. Does that kind of make sense? Because it's like, we said PF minus PI, right, as our delta P, right? So your vein has a pressure of 5 millimeters of mercury, or the 657.9 pascals. So that's like the final pressure, right, in your blood, essentially. But the pressure coming in due to this like saline solution and the difference in the height and whatnot, right, that will be 6,790. So it's like, this is what's coming out, right? Or like, I guess, okay, so this is like in your blood, and this is like out of needle, basically, right? So this is the pressure like here, 6,790 coming into your blood, and then your blood will have a final pressure basically of that 657.9. So delta P should be negative, yes. And I believe it should be like negative 6,132.1 pascals, if I'm not mistaken. Yeah. So they said that, and I just completely overlooked it once again. Difference in input and output pressures across the needle, right? So if the vein, right, that's just in your blood, right, here's the inside basically. If that's 657, right, that's like our output, I guess, essentially, and our input is like, due to the difference in the pressure, like based on the height, was 6,790. So like our input minus our output should give us our delta P, which is the negative 6,132 pascals. And we can convert that to millimeters of mercury by doing a similar conversion here, just the opposite. So we'll do negative 6,132.1 pascals, 10 to the 5th pascals is 1 atmosphere, and 1 atmosphere is 760 millimeters of mercury, right? So that should give us like negative 46.6 millimeters of mercury. And negative 6,132.1 pascals. So it's just calculating the pressure drop between the needle and your blood, right? So I have this needle coming in, right? And pressure at this needle right here coming in is like 6,790 is what we said, right? And then if we kind of like do a magnification, right, if it's our blood, so we can kind of imagine our blood, right, that has a final pressure, right, an output pressure basically of 657.9 pascals, right? So the needle, based on the height difference right here, right, is going to have an input pressure of 6,790 pascals, and then like the output right here, which is just the pressure of our vein, is going to be 657.9. Make sense? Yes? Okay, cool. But yeah, I know that I got confused myself, so hopefully that kind of cleared things up. Difference between the input and the output stuff. But part B now is asking us for the flow rate, right? This is a lot simpler now. Flow rate, which is Q, right? We know that to be area times the speed, right? But we also know it to be what? Well, that would just be, I think you're one step ahead. I think you're at C. That's when we would use the that equation, right? But for B, for the flow rate, we know that that's equal to area times the speed, but it's also equal to what? What other values? Yep, V delta T. So volume over time, right? So they gave us the volume here earlier. They said they had to inject 125 milliliters of saline solution, right? They said what? Over a 1 hour period, so that's our time there. So let's just plug and chug. So 0.125 liters per 60 minutes, right? That's just 1 hour. And then we can convert that to meters cubed per second, right? Because we want that in SI units. So we know that 1,000 liters is 1 meter cubed, right? So that liters cancels with liters. We have meters cubed on the top. And then with seconds, 1 minute is equal to 60 seconds. So that should give us around like 3.5 times 10 to the negative 8 meters cubed per second. Makes sense for the flow rate? Yes? Okay. But yeah, that's just volume over for time. So they released, or they injected 125 milliliters over a time period of 1 hour. Yeah. Now part C, right, where we use pressure drop equation here. So delta P is equal to negative Q times the radius, right? Or the, my bad, times the resistance. So that's this equation right here. And this resistance equation, we can actually expand that out a little bit more, and that'll include radius, which we can figure out here. So we know that the pressure drop was like, what was it? It's negative 6,132, right? So we have delta P is equal to negative Q times the resistance. We can solve for the resistance here, right? That's going to be delta P over negative Q. So it should be like negative 6,132.1 pascals over the negative 3.5 times 10 to the negative 8 meters cubed per second, right? And I believe that should give us our resistance value there. So negative 3.5, right? Yeah, that should give us around like 1.75 times 10 to the 11th. And that's like, what is it? Pascal seconds per meter cubed. Doesn't really matter because this is more of like an intermediate value, because we're going to be using this to then figure out the radius, right? Because we know that the resistance is equal to 8 times the viscosity times the length, right, over pi r to the 4th. So we can rearrange that. We can basically say like 8 times viscosity times the length is equal to like what? R times pi? Yeah. And then the fourth root of that is equal to the radius. So if we just multiply it over pi r to the fourth, divide it over r, and then divide it over pi, right? And then take the fourth root. Does anybody need me to like write this out in more steps so you can see it a little bit more clearer? Make sense? Okay. All right. So that gives us our radius here. So this is, once again, just kind of a matter of plugging and chugging. So fourth root, 8 times our viscosity, which was 1.1 millipascal seconds. So we kind of need to convert that to Pascal seconds, right? Which that's just going to be like 0.0011, yeah. Because that's just dividing by 1,000. Then multiplying by the length, right, which was 3 centimeters, which is the 0.03 meters, right? Missing anything else? I want to make sure. No, I think I'm good. So then we have our resistance, right, which is the 1.75 times 10 to the 11th, and then times pi. And if we throw that all in, let me recalculate it just to be sure. Oh, shoot. I actually legitimately don't know how to plug in a fourth root on my calculator, but I'll just take it to the 1/4 power. So 8 times 0.0011 times 0.03 over 1.7, 1.75 times 10 to the 11th times pi, and then all of that to the 1/4 power. Yeah, okay. So that should give us, I think 1.48 times 10 to the negative 4 meters. And then that's 0.148 millimeters. So you end up with SI units, but they want it to be in millimeters. So you'd have to convert that as well. Any questions about part C? Yes, that's a 4. Times 10 to the negative 4. Sorry about that. Funny, weird story. Totally unrelated, but I used to write my 4s like this. This was like first grade me. I was chilling. But then, for some odd reason, my first grade teacher, like, took points off whenever I'd write my fours like that, like on a addition or multiplication test or whatever. And she was like, you have to write your fours like this. And I was like, okay, all right. I think that was just me. That was first grade me trying to like write out my fours like the Fantastic Four after I watched that movie. So I was just going all, I was probably going crazy with the fours. But no, it is not. It's actually a great elementary school. But no, me and the teacher were good now. Like we're like really good friends. So no hard feelings. But it was just an odd like little pet peeve, I guess, that she had. So I don't mind it. No. But I also remember they had a thing. So this is another teacher. But they also had a thing with my twos. I remember. I don't know. I used to write out my twos like this, and I don't know. I don't know if they like made me do my twos like this, but I don't know. I just write my twos like this now. Yeah. Very like rarely will I ever like regress to my child ways and write my twos like this, and I'm like, second grade all over again. So sorry for the totally unrelated story, but I had like some flashbacks. So thank you, Kate, for confirming that's a 4 and for running back some memories. But yeah, that is a 4. Anyway, I think that's it for problem 3. Also, another funny thing, believe it or not, I remember this title here was different on the answer key when we had it last semester. So they changed it to just atherosclerosis, right? But the title was make atherosclerosis great again. But I figured maybe they didn't want to upset any people, I guess. But yeah, that definitely was the title last semester. So no, I just totally way. Yeah, they definitely had that the title. It was make atherosclerosis great again. Let me actually hold on. Let me see. Can I send screenshots or messages in this chat? No, I can't. Dang. Oh, I got cut off. It was make atherosclerosis great again. Yeah, they had Among Us on a quiz before, but yeah. Anyway, another one of those unrelated stories. And Tom and Jerry, I remember that. There was a written homework problem where Tom messing with Jerry again. Anyway. I know what I'm adding to my eval. Oh my gosh. Alright, so. Oh, wow. Ironic. So I now I understand. I didn't even realize this. But that's why the title was that. Because Donald's aorta was 8 centimeters long. Oh my god. Yo, they're mad disrespectful for that. Wow, that's man. De Jong is goated for that. Damn, throwing shade. All right, Donald's aorta is 8 centimeters long. I can't get past that sentence. With a diameter of 2 centimeters, and has had its radius reduced to 25% of its original value due to plaque deposits. The viscosity of the blood is 10 millipascal seconds. Oh my gosh. Okay. The original pressure drop across the artery with no plaque buildup was 20 pascals. what was the flow rate of blood through the artery before any plaque buildup? So, the original pressure drop was 20 pascals, right? And then they're asking us for the flow rate before any plaque buildup, right? So we know that pressure drop is equal to negative QR, right? So once again, just kind of plug and chug. We have 20 pascals on the left. We need to figure out Q. And we have the resistance here, which is the 8 times the viscosity times the length over pi r to the 4th. So I'm going to just write this out here real quick. Pi r to the 4th. And then rearrange things a little bit. So I have 20 pascals times pi times r to the 4th. And r was what? Diameter was 2 centimeters, so radius is 1 centimeters. So 0.01 meters to the 4th. And then divide by 8 times 10 millipascals, which is 0.01 pascal seconds, right? And then times our length, 8 centimeters long, so that's 0.08 meters. So, and that's just, the way I got this was, so I have 20 over here, right? So I need to figure out my Q. So I multiplied over pi r to the 4th, right? So I have that on top, and then divided over 8 times my viscosity times my length. And that should give me my Q there. And I think, actually, you don't even need this negative Q, because since it was a pressure drop, it should be negative 20 pascals. So the negatives will cancel out anyway. But that should give us a Q of around like 9.8 times 10 to the negative 5th, I think, meters cubed per second. But yeah. Oops, there, negative 5, there. That sound good to everyone? 9.8 times 10 to the negative 5. Yes, still triggered. Yep, me too. So probably move on to part B. Part B is asking, so now what is the new flow through the artery with the constriction, assuming the same pressure drop as before the plaque clog? So you have the same pressure drop, right? But now we have some constriction, right? So the radius is different. And then we're trying to see how that'll affect the flow. So what did they say? The radius is reduced to 25% of its original value. So you can just take 0.25 times the radius. So 0.25 times, what was it, 0.01? So essentially we can just like copy this over. It's the same thing, right? It's just that now this is like 0.00, oops, 25 meters to the 4th, right? Everything else stays the same. Because all that happened was that there was constriction, right, due to the plaque clogging, right? So the radius reduced to 25% of its original value. But yeah. Now that should give us like our Q as being 3.8 times 10 to the negative 7 meters per second. Meters cubed per second, my bad. There we go. So that's our Q, right? That's after the clogging, basically. There's a sizable difference there. So that man should stop eating McDonald's. Q and negative Q. So basically, since they said it was a pressure drop, so when the pressure drops, right, like there's a drop in pressure, your delta P is going to be negative, right? And the original equation is delta P is equal to negative QR. So if delta P is negative and we have this outstanding negative sign here, they're going to cancel out. And your final answer should be positive. Does that make sense about the whole Q, negative Q thing? Yep. Cool. Any questions about P? All good? Cool. Alrighty. So part C now is saying, what would the new pressure drop across this section of artery need to be to bring the flow up back to the original level? So we need to figure out a new pressure drop, right, to maintain the same amount of flow as we had before. So the flow that we had before was 9.8 times 10 to the negative fifth meters cubed per second. And we want to maintain that flow, but we have to do it at a different pressure, basically, or different pressure drop, right? So, and obviously we want to maintain like the, we want to maintain, but like basically the plaque is there, it's unavoidable. So we're going to maintain that clogged radius or clogged artery, right? So that with that reduced radius there. But now it's just saying like, okay, well, given that the plaque is there, given that the artery is constricted now, right? If we wanted to keep the blood flow constant, what kind of pressure changes would we need to make, right? So delta P is equal to negative QR again, right? But this time our Q is gonna be the same as before, right? So we want to maintain our levels before getting clogged. So negative 9.8 times 10 to the negative fifth, was it? Meters cubed per second. Yeah. And then multiplied by our resistance, right? Which was the 8 times 0.01 Pascal seconds times 0.08 meters over pi times 0.0025 meters to the fourth. And that should give us our new pressure drop. So once again, this is just saying that, okay, so my artery before any plaque had a flow of 9.8 times 10 to the negative 5 meters cubed per second, right? That was before getting clogged up. This was after getting clogged up, right? So there's a decrease in blood flow. If I want to make sure that this blood flow comes back up to its normal value before getting constricted, right? How can I do that given that my artery is now permanently clogged, right? So now that I have this artery has a permanently reduced radius from 0.01 meters to 0.0025 meters, right? So 25% of its original value. So that artery is clogged. It now has a radius of 0.0025 meters, right? If I want to increase this flow, if I want to make it go from 3.8 to 9.8, right? What kind of pressure drop should I have? That's basically what it's asking, right? And so if you do that, you should calculate the pressure drop to be around like negative 5,121.3 pascals. I think that's what I got. Yeah, so that's a big pressure drop. But it's accurate. Yeah. It's unfortunate, but it's accurate. Yeah, you're supposed to get big numbers. I think this is just throwing shade again to Donald. So there needs to be a large pressure drop to maintain normal levels of blood flow. See, that's where you have to make sure that you don't let like the big numbers or small numbers become a factor in like feeling like you did a problem incorrectly or not. I mean, it's a double-edged sword, because sometimes like the problems, you'll read them and you'll be like, okay, well, you kind of consider the nature of the problem, or like the situation or the environment that's going on, right? And so like if you get a really big number and you're like, okay, that doesn't match up with like the rest of the story, then you're like, okay, that's crazy. That you can do kind of like your sanity check in that sense. But sometimes the nature of the problem is just insane. Sometimes they mention it, sometimes they don't. And so that's when your like intuition and your sense of like, okay, is this value actually making sense or not, that kind of fades away. Because I mentioned this before, we had like a problem about like viscosity and a toaster flowing through honey, right? And apparently the toaster belonged to like a fairy or something. And so we got like really, really small viscosity values. And just like values for everything, to be honest. Like all the values were really small. We were all confused because like we were like, how small is this toaster? Because the picture was literally like, picture was like this, right, in a beaker, and the toaster was literally like giant. So it threw everyone off. Like, okay, this toaster appears to be big, but we're getting really small values. So anyway, it's just like you have to kind of make sure that you're applying your concepts correctly. And I guess to a certain extent, that's a little bit difficult, because if you mess up or if you're not sure, like doing a sanity check is sometimes the way to kind of reassure your conceptual thinking, but sometimes it doesn't work. Yes, the toaster was in honey and in a beaker. Don't ask, because actually, you know what? I'll show it to you at the end of the end of the session. It might have been for a fairy. I don't know. It definitely was like a tall tale. It's just not real. Like no way could you have a. I do have the exam. There was the second exam, I think. It might have been the first one. I can't remember, but definitely was crazy. So one sec. Let me pull that up so I remember to show it to you guys at the end of the session. But yeah, that was probably the craziest problem that we got last semester. Midterm exam 2, I think it was. Nah, hold up. Might have been exam 1. Yeah, there we go. Got it. Yeah. It was a bucket of syrup. My bad, not a beaker. But regardless, yes, we are doing D. I was pulling up the crazy problem. I'm sorry. So, all right, last part, and we should be done for the day. What? That's bogus. This was optional, not for credit. No, hold up. No. This is the optional part. Yeah. No, not the whole problem. But yeah, I'm not doing it either. I don't think I did it either. But okay, so it says, assume that Donald has had the plaque buildup given above, with all other blood vessels remaining unchanged. Originally, his blood pressure was 110 millimeters of mercury, but it increased in order to keep the flow through the artery at its pre-clog rate. Compute Donald's new pressure, and determine what level of hypertension he is at. So, so the original was 110, right? And then we said, we had a pressure drop that was needed in part C to bring it up to the original level, right? So his new blood pressure, I think, would then be, so it'd be new blood pressure would be 110 millimeters of mercury, right? And then oops, forgot the G. So we had a pressure drop. Okay, so and this should have been, I guess. Well, it doesn't matter. Okay, so delta P from before was 5,121, I think, pascals, right? Yeah. So if we convert this to millimeters of mercury, we should get around like 39 millimeters of mercury, I believe, right? So he needed to increase that, he needed to increase his pressure, right, to keep the flow the same. So this is basically saying, like, what's his final pressure now based on this, like, pressure drop. So he had 110 from before, right? And he needed to increase by this pressure drop to keep the flow at its pre-clog rate. So it was essentially just 110 plus 39 millimeters of mercury to give us 149 millimeters of mercury, which I think it's a little bit confusing, but I'm trying to think how to explain this a little bit better. So, okay, what would the new pressure drop across the section of artery need to be to bring the flow rate back up to the original level? So, I guess pressure drop, okay. Man, okay. I guess, like, this is the difference in pressure, right, across the artery, and we know that that's 39 millimeters of mercury. So it's like saying I would need to factor in or add that difference in pressure to the original pressure to ensure that the flow remains the same. So it's like, I guess, remember how we saw that it went from 20 pascals to 5,000 pascals or so, right? So in order to maintain the same flow rate, you would kind of have to increase that pressure drop, and that pressure drop is what we're adding to our just original base, like, pressure value to get our new blood pressure. Does that kind of make sense? I don't know. I don't like that explanation. Yeah, it would be 149 millimeters of mercury. And I guess just to add this as well. So by the way, 149, that'd be what? He's in stage 1, hypertension. Stage 1 is above 140, stage 2 is 160 plus, but so yes, it's stage 1 hypertension. But I guess let me think about it as like, okay, if delta P is P final minus P initial, basically, right? Okay. So if my delta P was like 5,121.3 and my initial was 110 millimeters of mercury, basically. Okay, that makes a lot more sense. All right. Yeah. So if I just ignore like the negative signs and I just go to like, if I think about just absolute value, right? Delta P is equal to your final pressure minus your initial, right? So it's saying like, this is my initial. Well, let me do a different color. So it's initial, final, right? So initial right here, like this part right here is unclogged, right? So it has to go through this clogged area, right? All this plaque to get to some final pressure, right? So the change in pressure, like the pressure drop from here to here, right? From this initial where it's unclogged to this final where it had to go through the clog, right? That change in pressure to maintain the flow, we said was 5,121.3 pascals, right? That's 5,121, right? That's equal to the final minus the initial. Well, if the initial, where it's unobstructed, basically, right? Where it's flowing normally, right? You can just imagine like the continuation of this artery. Everything's flowing normally. If that's 110 millimeters of mercury, right? We can essentially calculate the final blood pressure, which is here, like after the clog, right? Or like basically just at the at the end of the clog, essentially. So we can take the 5,121 pascals, convert that, and we said that that was going to be 39 millimeters of mercury. So if we add this to that side, we should get our final pressure being 149 millimeters of mercury. Does that make a little bit more sense, like relating it to equation? And the reason why this is positive now, instead of being a pressure drop, right, is because they had said that the pressure, so they said, okay, original pressure was 110, but it increased, right? So if the pressure increased, so our final blood pressure is actually greater than our initial. So if this is greater than this, then your delta P is actually positive. So it's like taking the absolute value of it, or like the magnitude. 39 millimeters of mercury is the conversion of 5,000 pascal, like 5,121 pascals to millimeters of mercury. Oops, sorry. So if we took this value here, 5,121, and converted it to millimeters of mercury, we'd get 39 millimeters of mercury. And so if we plug that into the equation here, so we know that the delta P is 39. Our final pressure is what we're trying to figure out, and our initial was 110. We can add that over, and we can get 149 millimeters of mercury as our final pressure. And that's his new blood pressure, basically. Does that make a little bit more sense relating it to the equation? You didn't get 5,121, you got 5,110. Let me recalculate real quick. -9.8 times -5, okay. And then multiplied by 8 times 0.01 times 0.08 pi times 0.025 fourth. Oh, I see, my bad. I rounded at this point. I got negative 9.8. I had initially a negative 9.82, so I think I just plugged in like my answer from like my original answer from this part without rounding and plugged it into here, and that's why I got 5,121.3. So I made the mistake of rounding. But yeah, if you plugged in everything that I said here, you should get 5,110. But if you did negative 9.82, right, which is closer a little bit to what we got for A, then yeah. And if you go ahead and convert, 5,110 or 5,121, either one, I mean, it's a difference of 10 pascals, which isn't that great. And if you convert it to millimeters of mercury, you still get about 39, I believe. Yeah, 38.8, 39. So, does that make sense, though, the whole delta P thing? Like your final minus your initial pressure? Because they said the pressure increased, right? So we know that the pressure drop, this pressure drop, definition of drop means like there's a negative change in pressure, right? But this is also equal to PF minus PI, right? Now, they said that his pressure increased, right? So if his pressure increased, then this pressure drop, like the magnitude of it is the same. But since if it increased, that means that your final is greater than your initial, then this becomes positive, basically, right? So that becomes positive, right? We can kind of plug things in, 5,121 or 5,110, whatever you got. This is your final. This is your new blood pressure. This is your initial, which is the 110 millimeters of mercury. We converted this to 39 millimeters of mercury. And if we add that over, we should get our new blood pressure is 149 millimeters of mercury. Does that clear things up a little bit? And he's in stage 1 hypertension based on like the criteria that they had in the parentheses here. Yep. Oh yeah. So I guess if that's it for problem 4, if you guys don't have any other questions, I can show you the problem real quick. Yeah, for sure. But any other questions about these problems at all? And please remind me if I forget to upload problem 1 to the drive, remind me to do so. But yeah, I will go ahead and end the recording here.